Okay, we're talking about absolute value functions. Here's a graph, your basic toolkit function. Slope of 1 here, slope of -1 over here, that's going to be important. And we can transform the toolkit function. Here's our toolkit function. We can take this thing and translate it over here, translate it up here. Here's a toolkit function. Transform. Here's a toolkit function vertically stretched. Here's a toolkit function that's the same as this one, but inverted and then shifted over and up. So we have this general picture, and if we understand transformations, we can sketch these graphs. And these graphs are going to turn out to be kind of useful to visualize certain things about absolute value equations and inequalities. General forms are transform functions. If you do absolute value of x plus k, it's a vertical shift. A times absolute value of x is a vertical stretch. X minus h is a horizontal shift, h units. And A times absolute value of x minus h plus k is all three. Now, an absolute value inequality. Absolute value of x minus 3 less than 4. You should be able to see this better than you did on the Zoom link. But here is, in green, our absolute value of x minus 3. That's the absolute value of x shifted over 3 units. Still has a slope of 1 here, slope of -1 here. Now, here's the line y equals 4. Here's all the points for which y is less than 4. That's kind of shaded. Now, to say that absolute value of x minus 3 is less than 4 is to say that the y-coordinate on this graph of absolute value of x minus 3 is below the line where y equals 4. So all the points that satisfy this inequality can be represented by all the points on the graph for which absolute value of x minus 3 is less than 4 lie on these two orange segments. The x values that correspond to those y values, in other words, the values of x that give you points where the absolute value of x minus 3 is less than 4, lie on the purple segment, which runs from the projection of this point down here to the projection of this point down here, or from this one to that one, either way. Okay? Well, that means that these x values are the x values that make this true. So those x values are the solutions of this inequality. Well, where are those x values? The point of this, the vertex, if you wish, of the absolute value function is shifted from x equals 0 to x equals 3. So x equals 3 at this point. Okay, now I've got 4 here for some reason, but I don't think it needs to be there. Okay, so x equals 3 here. The slope of this graph is 1, and the rise from the x-axis up to y equals 4 is 4, which means that the run here also has to be 4, so that the rise divided by the run is 1. So that from here to here, the distance is 4. Similar argument on this side. Now the slope is -1, so a rise of 4 would correspond to a run of -4. So here's your -4. Okay, so we can see that the purple interval, which represents all the solutions of this equation, runs from 3 minus 4 to 3 plus 4. Okay. Now there's some comments here, but that's the way it comes out. By the graph, the purple interval runs from 3 minus 4 equals -1 to 3 minus 4 gives you negative 1 to 3 plus 4, which is 7. So we have negative 1 here and 7 here. And it's an open interval from negative 1 to 7. Another way to write that, the set of x such that negative 1 is less than x less than 7. That's a proper way to express this thing as a set. But sometimes we just write the inequality, negative 1 less than x less than 7. Okay. Now there's more. We'll do that in a separate video.